Welcome to the Cadence Design Systems Pointwise tutorial. In this video, I will show you the full Pointwise workflow in a simple case. We're going to import a geometry, generate a surface grid, generate a viscous volume mesh, set up the CA boundary conditions, and export the final grid in Omnis format. The geometry we're going to use in this tutorial corresponds to a simplified quadcopter. When you open Fidelity Pointwise, you're going to be presented with a screen that looks like this. Keep in mind that here you can, for example, move things around different toolbars to different locations if that is what you want to do to basically suit your particular needs. So let's go ahead and get started. The first thing I'm going to do is go to the File menu option right here, and I'm going to click Open. I'm going to navigate to wherever I have my initial Pointwise file. In this case is right here, and the file is called quadcopter-asm-avm-initial.pointwise. I'm going to select that and open it. In just a few seconds, the geometry is going to open in Pointwise, and as you can see, we have a simplified version of a quadcopter. Actually, we have half of that quadcopter. Before we start, I would like to mention that this geometry has already been prepared for meshing. Now, what do I mean by that? So you can actually see right here in the List tab and the database option, if you expand these, you can see that I have a single database model. That is the first step in preparing your geometry for meshing. You want your geometry to be a single watertight database model with no gaps. You can actually do that in Pointwise, or you can do that in your CAD package. The next thing that you have to do after you have a single watertight solid model is basically assemble quilts together to define the appropriate meshing regions. You can see that some of the quilts have been colored in different colors right here to make things a little bit more clear. But one thing to keep in mind is that Pointwise will generate a single domain per quilt. If you want to learn more about assembling database models and assembling quilts, I do recommend that you check the PDF version of these tutorials, as I have added appropriate links to the appropriate pages in the Pointwise user manual. Now that we know that the geometry has been cleaned up and is ready for meshing, let's go ahead and get going with the meshing process. The first thing that you need to do is to check your current CA dimension and to also check your current CA solver. You can find this information down here in your Pointwise GUI. As you can see, the current CA dimension is set to 3D, which is appropriate for this case as we're going to be generating a 3D volume mesh. And your current CA solver is set to CGNS. Now, what do I mean by your current CA solver? If you set up the appropriate CA solver that you're going to be using to run your simulation in Pointwise before you actually start generating any grid entities, Pointwise is going to make sure that all the grid entities that are generated are appropriate for that solver. In addition to that, Pointwise is going to allow you to set different CA boundary conditions, and the physical types for those boundary conditions are also going to be appropriate for that CA solver that you're going to be using. Now, how do we actually change the current CA solver? I'm going to go to CA and select solver. And as you can see, we have a long list of appropriate CA solvers that we support. And the current solver is set to CGNS. And this is indicated by this green chevron right there. And we're going to change that to Omnis. So I'm going to scroll down, look for Omnis, and double click right here, and two things are going to happen. Omnis is going to be set up as the current CA solver, and this panel is going to close. However, you can see down here again that now Omnis is the current CA solver. So let's continue with the generation of the mesh. At this point, we're ready to simply select our database model, and to select something in Pointwise, small side note, you need to make sure that the appropriate mask is actually checked on. In this case, we want the database mask checked on because we're selecting a database model. So I select my model and I go to Create Automatic Surface Mesh. As you can see, the automatic surface mesh functionality has three tabs: the global tab, the surfaces tab, and the boundaries tab. You can also see these tabs have several parameters right here, and those parameters have default values. Now, those default values are set up based on our understanding of the best practices for creating surface grids. In our case, most of these parameters are going to work fine. We're just going to change a few of them to generate an appropriate surface mesh for this geometry. If you want more information about all of the parameters that you have in this functionality, I do recommend that you check the PDF version of this tutorial, as I have added links to the appropriate pages of the Pointwise user menu. So in our case, we're going to change this number right here. The max aspect ratio has a default value of 10, and we're going to be changing that to 20. Now, the max aspect ratio is that parameter that basically limits the aspect ratio of the anisotropic cells that are created on the surface grid. And we're changing that number from 10 to 20 to relax our grid a little bit for this particular demonstration. Another thing that I would like to point out here is in this section, the display frame, you can actually see that we have some quality metrics listed in there. In particular, we have the area ratio, the aspect ratio, and the max angle. Now, another thing you can see is for each one of these metrics, we have a threshold that has been defined, and this again is based on our best practices. And once the surface mesh is actually created, any cells that do violate this threshold right here, they're going to be listed right there. So we're going to show you how many cells, if any, actually violate those thresholds for these metrics. And last but not least, we're going to also display the maximum value for those metrics for the entire surface grid. So this is a really handy way of actually having right here in the same functionality information about some of the appropriate quality metrics for the surface grid. So let's move along. I'm going to click the Surfaces tab, and in here we're only going to do one thing. We're going to be creating a new mapping filter. Now, this mapping filter is going to allow us to force the number of grid points that we want in the surface grid that is created on the blunt trailing edges region. So let me change my view a little bit in this geometry, and you can see that all of these blades have a blunt trailing edge. For some CFD simulations, it's actually very nice to be able to define the number of grid points that we want across that trailing edge. In our case, we're going to define 5 subdivisions, meaning 6 grid points across the trailing edge. And in order to force this number, we need to create a new mapping filter. How do you create a new mapping filter? First thing, you click New, and you can actually see a new row has been created. Next, we're going to double click on this particular cell right there under the name column, and we're going to set up an appropriate name for this particular filter. In my case, I'm going to put trailing edges. Now, the next thing you have in here is the pattern, and this is going to decide which entities are actually assigned to that particular filter that you're creating. So there are 2 ways to assign entities. You can simply select the entity, meaning the database quilts, from the display window and then click on Set right here. And as you can see, that particular quilt has been added already. Another way to do it is basically to make sure that those database entities have a name that follows some common pattern. And if that is the case, you can define that pattern right here, and all those entities are going to automatically be assigned to this new filter. In my particular case, I'm going to define this pattern right there because all of the names of these quilts on the blunt trailing edges for all of the blades, they follow a pattern that have the TE name in it. So if I specify this particular pattern, they're all going to be recognized, and as you can see, they're going to be automatically added right there to this particular filter. Zooming out a little bit, we can actually see another interesting point right here. If I select my new filter, you can see that this filter is color coded in orange, and all of the blunt surfaces have also been color coded in orange, and makes it very easy to see. Let's continue with the definition of this new filter right here. The next thing we have to do is choose the appropriate type. In our case, we're going to choose the force option right there, because I do want to force the number of subdivisions that I want across the trailing edges, and in this case, we're going to be setting that to 5. So at this point, my filter is all done, and that is all that I have to do in the Surfaces panel right here inside the Automatic Surface Mesh functionality. Again, if you want more information about the different options and functionality that you have in here, I do recommend that you check the Pointwise user manual. Let's go ahead and move to the Boundaries tab, and you can see right here that we have a table, and Pointwise is actually automatically identifying edges and coloring them appropriately in different ways. There are edges that are identified as curvature edges, some other ones are convex, and some other ones are concave. In our case, we're interested in the convex edges, which are those purple edges that you see rendered in there, and what we're going to do is turn off the generation of stretched cells or anisotropic cells off of those edges on the surface grid. For this particular case, we do not need them, so I can simply double click right here and turn them off. Going back to the Global tab, I'm going to go ahead and change the view a little bit, and we're basically ready to generate the surface mesh. One additional thing that I want to show you before we actually generate the surface grid is how you can use this function right here, show size fill, to basically get an idea of what your surface grid is going to look like. So let's go ahead and click on that. In just a few seconds, the size fill has been generated for your entire geometry. And what I want to show you here is, if I zoom in a little bit close, if I move my mouse pointer around, you can see that you have a little cell right there where you have the mouse pointer. That cell is going to give you two pieces of information. First, it's going to give you the type of cell that is going to be created. In this case, your entire surface grid is going to have triangles. And the second piece of information is it's going to give you an idea of the cell size that you're going to have in that region. If I go ahead and move along across this geometry, you can actually see that the size of this cell is going to change for different areas. Right? It's going to become smaller or larger. Of course, if you move close to the blades, you're going to want more refinement in there, and the size of your cell is going to be smaller. So again, this is a very nice way of getting an idea of what your surface grid is going to look like without actually creating the surface grid. Going back here, I'm going to click on Hide Size Fill, and the next thing is create the surface mesh. Okay, our surface grid has been created based on the specification of the different parameters and all our settings. So let's see what we got. I'm going to zoom a little bit closer to areas of interest, like for example right here. You can see right there that we did have that enforcement of the number of cells that we wanted it across the trailing edge. In our case, we have 6 grid points and we have 5 subdivisions. So that is actually very good. If you get closer to this area right here, you can also see that we do have a very nice stretch or anisotropic cells that allows us to capture the curvature in these regions, but at the same time minimizing the cell count. So this is exactly what we're looking for here. And this is a general view of the mesh. In general, you can also see that you have larger cells when there's not a whole lot of physics going on, and you have smaller, more refined surface grids in areas where there is more physics happening, and in areas where you actually want that kind of refinement. So another thing that I want to point out before we end the surface mesh is if we go right here to the area where we show you the metrics, let's take a look at what happened with the different metrics. So you can see the aspect ratio and the max angle. We have 0 cells that actually violate the thresholds that have been specified, and you can also see the max values right here for those two metrics. However, you can see that for the case of the area ratio, we do have a number of cells that actually violate that threshold that has been defined. It's not violated by a whole lot. We're actually in about like 12 or 13, and the threshold was set to 10, but they still violate it. So let's take a look at those areas, and I can actually do this by checking on this option right here, and you can see in the display window that these cells that violate these metrics are going to be rendered in red. If I get a little bit closer, you can actually see what is happening right here. You have stretched cells on the blunt trailing edges, but then on the surfaces, you have pretty much anisotropic cells. Even though the area ratio is not super big in this case, it is a little bit larger than we would like it to be. Now keep in mind that if you create a volume grid using this surface grid, that grid is going to be in general of good quality, and you're going to be able to run it in your CFD simulation. However, I want to show you how you can actually improve this particular area to reduce the area ratio. So we're going to be doing this outside of this functionality. At this point, my surface grid is ready, and the only thing that I have to correct is that particular area, and I'm going to show you how you can do that. So I'm going to click OK. I exit the functionality, and now my grid has been saved, and I'm going to change some display settings to basically reduce clutter just a little bit. So the first thing I'm going to do is go to View and check the Show Database option right here to turn off the display of database entities. The next thing I'm going to do is select all my domains by clicking up here and go to View Attributes. And I'm going to change the fill option to hidden lines, and then update entity display and close. As you can see, that changes the display a little bit to make things a little bit easier to understand. Now, let's go ahead and take care of that area ratio situation that we mentioned before. What I'm going to do this is to select all 8 surfaces, the upper and lower surfaces of the plates. The way to do this is you move your mouse pointer to one of those surfaces and you click on the left mouse button. And I'm going to get a little bit closer so you can see what happens. With the mouse pointer right there, you can hit the space bar and you can see that now the lower surface has been pre-selected. So I can click or hit the control key and left mouse button again. At this point, 2 the upper and lower surfaces have been selected. Now let's repeat this process for all the other blades, and we're going to have our selection. At this point, I have 8 domains selected. So let's go to Grid, Solve, and we're going to go to the Boundary Conditions tab right here. And what I want to do is to create a new boundary condition. Let me change the view right here a little bit. I'm going to create a new TRX boundary condition so I can actually create anisotropic cells growing off of these edges right here, these connectors right there. And that is going to have a much better transition from the blunt surface grid to the rest of the surface grids right here. So to create a new TRX boundary condition, I'm going to click the New button. And then the process is very similar to what we have seen before. I'm going to double click here on the name and set a new name. And right here, I'm going to double click here and select the appropriate type for this boundary condition. In this case, it's going to be adjacent grid. So the adjacent grid boundary condition, what it's going to do is create anisotropic cells on this surface right here, but it's going to use the initial spacing of the adjacent grids, which is the blunt trailing edge surface grid that we have right here. So that is going to give us a really nice transition between this surface grid and the one up here. Now that my boundary condition has been created, the next thing that I have to do is to assign edges to it. So the way you do it is you put your mouse pointer right on top of these connectors right here. You click the left mouse button. I'm going to move to the next one right here, control click and left mouse button. And I'm going to do the same with all the other blades. I'm going to rotate a little bit and select all of those edges right there to create my anisotropic or stretched cells. Select this one, and I have two more to go. This one and this one. I have now 8 edges that have been selected. Once the selection is complete, you're going to click on this set checkbox for that new boundary condition you have created. And you can see that 8 edges have been assigned. You can also see that you have the color coding here is yellow, and that corresponds to what you see in the display window for all those edges assigned to this boundary condition. Next, let's click on Solve and simply click on Refine. What this is going to do is it's going to refine those 8 surface grid that you see selected right there and render in white, but it's of course going to apply the new settings that you have, which is the new T-Rex boundary condition. I'm going to change my view so you can see the effect of this new T-Rex boundary condition. I'm going to move a little bit closer to the area where we had that situation with the area ratio, and we're going to let the solver run. Alright, the solver has run, so I'm going to click OK to see what I got, and you can see immediately how the situation has been improved. You can see that there's a really nice transition when you look at the size of those cells from the blunt trailing edge onto the other surfaces on these blades. Let's go ahead and select all the domains once again, and I want to check the quality of my surface grid to actually make sure that that situation with the area ratio has been resolved. So I'm going to select all my domains and go to Examine and Area Ratio. The metric is computed, and as you can see right here and also in the color bar, the maximum value for this metric used to be 12, but now with our changes is 3.2, so that is certainly below 10, so this is very good. Let's hit close and we exit the metric, and our surface grid is now ready to go. With the surface grid now complete, we're ready to generate the volume grid. So to start that process, let's go ahead and once again select all of the domains and go to Create Automatic Volume Mesh. As you can see, you're presented with two options. The first option right here is Create Volume Mesh Boundaries, and that is the option that we are going to be using as we want to create the boundaries of the volume grid that we're going to be creating. The second option right here is called Use Existing Volume Mesh Boundaries. So if the boundaries of your volume mesh are already defined, you can use that second option since you don't need to create any additional domains. In our case, like I mentioned, we're going to be using the first option. So entering the automatic volume mesh functionality, you can see that a few things here are happening. So the first thing you can notice right there is that you have a very small box around your surface domains. That is the extent box. It's the smallest box that you can actually create that contains the entire surface grid, and it's called an extent box. The second thing that you can see is that an initial far field has already been created for you. Of course, for this case, we're going to be modifying this. And you can also see, I'm going to clear this axis right here. You can see that we have the H, W, and L axis, and we're going to be using those axes to define the size of our far field. So let's go ahead and take a look at the panel. You can see that you have again 3 tabs: the global, boundary conditions, and advanced. In our case, we're going to be very small changes to the numbers that have already been defined by default in this functionality. If you want more details about all the options that you have in the automatic volume mesh functionality, I do recommend you check the PDF version of this tutorial, as I have added appropriate links to the appropriate pages in the Pointwise user manual. So I do recommend that you check out that information. So the first thing we're going to do here in the global tab, we're going to set the type of the volume grid that we want to create. In our case, is going to be a voxel volume mesh. The second thing, we're going to be defining the shape of that far field. In our case, we want a box, so we're going to be checking the first option. And as you can see, you can also create a cylinder or a sphere. The third option right here is where do you want the center to be. As you can see, and I'm going to zoom in a little bit closer right here, with the first option selected, those yellow axes start at the sides of that extend box. And that is the option that we're going to be using. You can actually click on this second option right here, and you can see that if you do that, now the yellow axis start at the center of your geometry. In this case, that is the center of our symmetry domain. But like I mentioned, we want this first option right here. The next thing that we're going to be doing here is to basically define the size of our far field. And these are the margins that we want. We're going to enter 500 right here for L1 and L2. We're going to enter 300 right here for W1. You can actually see that W2 is actually grayed out, and that is because Pointwise is already recognizing that where W2 would be, you actually have a symmetry plane right there, so you don't need W2. And the third thing right there is the H1 and H2 margins, and we're going to be setting that to 500. So after you do that, you have a very nice preview of what your far field is going to look like. Small disclaimer, if I was actually generating a volume grid for an actual simulation, my far field would be a lot larger than this one. We're creating a smaller one just to show you the mechanics of how you can do this, and for the sake of simplifying this tutorial a little bit. Since we want to create a viscous volume mesh, I'm going to need a boundary layer. So I'm going to click in here and turn on boundary layers by selecting the geometric growth option. You can see again immediately you're presented with additional options. Those options have default values that are considered really good values based on our experience of good practices. And we're going to modify actually only one of these values, which is going to be the wall normal spacing. So that is going to dictate the initial spacing of my anisotropic volume cells off of the surface grid of that quadcopter. I'm going to change that number from its default value of 0.1 to 0.001, so 1e to the minus 3, and that is the only change that I want to make in this case. Again, if you want more information about the additional options that you see right here and what they mean, I do recommend that you check the Pointwise user manual that you can find online. Let's go ahead and move to the boundary conditions tab. And one of the beautiful things about this functionality that is going to save you quite a bit of time is, as you can see, boundary conditions are already defined and populated for you. One of those boundary conditions is the boundary layer. It has 47 domains assigned to it automatically. I didn't have to do anything. And you can see those are, of course, the surface grid that I have on my quadcopter. The type of this T-Rex boundary condition is wall, and I have my specified spacing right there. So anisotropic volume cells are going to grow off of this surface grid, and that is going to be the initial spacing that the software is going to use. Another boundary condition that has been already defined and pre-populated for me is the symmetry boundary condition. As you can see, it's highlighted in that cyan color right there, and Pointwise automatically is correctly identifying that symmetry plane that I have in my geometry. As you can see, we have half of that quadcopter. So I don't have to make any changes in this particular panel. Moving to the Advanced tab, I want to show you once again that Pointwise has correctly identified one of my symmetry planes, which is this one right here as expected. And you can see that the appropriate bounding edge of my surface grid has been, of course, correctly identified and is rendered in green to make it easier to see. So again, I don't have to make any additional changes in this particular tab. Let's change the view a little bit and let's go back to the global tab right here. So the next thing I have to do is simply create the volume mesh. So I'm going to click this button right here. And Pointwise is going to use all the settings that we have defined in the functionality to create the volume mesh. Very quickly, the volume mesh has been created, and it's important to keep in mind that at this point, the volume grid is there, but it doesn't contain any interior cells. And for that, it needs to be initialized. If you want to initialize it, what you can do is simply click on that checkbox right here that says Populate Volume Mesh on command completion. So what is going to happen with that checkbox checked on is when you click the OK button, this functionality, the automatic volume mesh, is going to be closed and your volume grid is going to be automatically initialized without you having to do anything else. Now keep in mind that depending on the size of your grid and depending on what kind of computer you're using, this process might take several minutes. Let's click OK. As you can see, the functionality was closed and now the volume grid is being initialized. All right, the volume grid has now been populated with cells. And the next step in the process is to actually check the quality of this volume grid to make sure it is appropriate for your solver. So with the block still selected, I'm going to go to Examine. And as you can see once again right there, Pointwise offers a lot of different examine options, examine functions that you can use. In our case, we're going to be using the maximum included angle function. You have in here quite a bit of information, but what I want to bring your attention to is the maximum extrema for this particular metric, that is 174. Now this volume grid as is with this kind of metric is going to run just fine is in most commercial solvers. However, we can actually improve this a little bit and I'm going to show you how in just a few minutes. One thing you can actually do here is, of course, enable cutting planes. So if you want to take a look at what your grid looks like in different regions, okay, you can create an X, Y, Z cutting plane and you can use those arrows to change your cutting plane as desired. To basically look at different parts of your grid, you can zoom in and see what your grid looks like in different areas. Of course, in here, this being one of the blades, you can see those beautiful anisotropic volume cells are growing off of the blade as expected. And then once you're done, you can simply click on Enable Cutting again, and that is going to disable the cutting plane functionality. Once we're done with the examine functionality, we're going to hit Close to close it. And I want to show you here how you can further improve the quality of your volume grid. With the block still selected, I'm going to go to Grid, Solve, and you're going to see right here that you have a smooth option. So Pointwise actually offers a smoother that will allow you to actually smooth your volume grid as desired. So in order to set this up, we're going to go to the Attributes tab, and I'm going to click on the smoothing option to expand the different options. Again, if you want to learn more about all these functionalities, I do recommend that you check the Pointwise user manual, where we have a really nice description of every single one of the parameters that you see in front of you. But I'm going to change the cost angle threshold, which is another way of measuring the maximum included angle. I'm going to change that to 170 degrees. The default value is 175. So what this is going to do basically is going to dictate which cells are actually going to go through the smoothing process, and those cells are going to be the ones that have a maximum included angle or a cost angle that is actually above 170. So in our case, all those cells have an angle between 170 and the 174 maximum included angle that we saw in the examined metric. Those are the ones that are going to get smoothed. So with these numbers set up, let's go back to the Solve tab. We're going to run these for 100 iterations and simply click on the Smooth button. After just a few seconds, Pointwise is going to run the smoother, and what I would like to do now is to go back to the examine functionality and check the exact same metric, the maximum included angle, to see if things actually improved a little bit from the 174 extrema that I had before. So you can see, still inside the grid solve functionality and still inside the solve tab, down here you have a way to directly access the examine functionality. So I'm going to click here and look for the maximum included angle functionality, and then I'm going to click on examine, and this is going to open the examine functionality once again, but now is done that from inside the Unstructured Solver. As you can see, once again, if you look at the metric right here, the extrema is now down from 174 to 171. So this is extremely appropriate for most CFD solvers. So with that done, I'm going to click close and OK. And now my volume mesh is finalized. Now that the volume grid has been finalized, we are ready for the last part of the mesh generation process, and that is to set up CA boundary conditions and then to export your final grid. So let's go ahead and set up the boundary conditions. For that, I'm going to go to CAE, Set Boundary Conditions. And as you can see, you have in here a table, and this is where I'm going to define my new boundary condition. So to create a new boundary condition, I'm going to click New. And the next thing you have to do is double click on the cell under the name column, and I'm going to define a name for this boundary condition that I just created. In this particular case, I'm going to put far field, and I'm going to select right here by double clicking the appropriate physical type for this new CA boundary condition, and in this case is also going to be far field. Remember, all those boundary condition types you just saw, they're appropriate for our current CA solver, which, as we see down here, is set to omnis. The next thing is I'm going to assign the domains that are going to be applied to that particular boundary condition using the selection techniques that we have discussed before. I'm going to select all the domains of my far field block except that symmetry domain. Once all my domains are assigned, the ones that I'm interested in, I'm going to click the Set checkbox, and I can see now, once again, that things are color-coded and those domains have been assigned to the boundary condition. Let's repeat the process for the other boundary conditions. Alright, my CA boundary conditions have been defined already, and as you can see, the appropriate domains have been applied to each one of the boundary conditions. Once this is done, I'm going to simply hit close. And at this point, I'm ready to export my grid. So I'm going to select my block and go to File, Export, CA. Just look for a place where you would like to save the new file, set a name for it, and simply hit Save. You have some options in there to decide how you would like to export your grid. In my case, all the default options are appropriate, so I'm going to simply hit OK. Alright, my volume grid has now been exported in a format that is appropriate for my current CA solver, which is Omnis. That is the end of the process. One last thing I would like to show you is keep in mind that it's always a good idea to save your work as you go. So the way to actually do this, you go to File, Save As, and I'm going to put an appropriate name right here for my final grid, and simply click Save. This wraps up our Pointwise tutorial. We walked through the entire pre-processing procedure from the initial geometry to the final volume grid in your desired CA format. Thank you very much for your attention.